talk. It's a bit of a change of pace since I've been listening to Nate for the last 3 days, primarily. You can listen to me for a little while. By way of introduction, you know I'm Kevin Stanley. Nate introduced me yesterday. I have been doing sensors for a long time. I have done sensors from the bottom to the top, sideways and backwards, upside down, and inside out. And lately I've been working on smartphone sensors and how they can be used to analyze human behavior. At dinner last night, Andrew mentioned that from his point of view, kind of Ethica is about surveys, and then we get all this other stuff for free. I've always looked at it the other way around, even in my background, that it's all about the sensors, and then, hey, once in a while we can pop a survey. Isn't that awesome? So I can't give you 20 years worth of sensor intuition in the next 20 minutes. But I can give you at least a little bit of a view of what these sensors are actually doing, how they physically work, and what that means in terms of how you can interpret the data. So really this presentation should be focused primarily on kind of what the sensors are, what the physical processes are that actually create the sensors, and what kind of failure modes exist. So when you're looking at the data, you can tell the difference between an outlier and a mistake. Make sense? Maybe I'm going to have to press the space bar. So no presentation is complete without a picture of a cat. So Icon has data. So as we've said before, the move is afoot to switch from a survey-based, one-off measurement of participants in the social sciences and health sciences to more continuous monitoring. And this continuous monitoring often depends on sensors, which are generally outside of the field of expertise of the people who know about the things that they're trying to measure. Mohammed gave you an overview of the kinds of sensors that Ethica currently measures. I'm going to do the same kind of thing, but I'm going to cluster them a bit differently. And I'm going to cluster them based on the physics that underlies these sensors. Because sensors are actually physical systems. We call them transducers. The formal definition for a transducer is a mechanism which takes one form of energy and transforms it into another form of energy. By and large, sensors are transducers which take some kind of physical energy, many, many forms, and turn it into electrical energy, which we can then easily handle inside a computing environment. Right? We can pass it through an analog to digital converter. We can count it with a counter. There are all kinds of different ways of turning this into a number once it's an electrical signal that we can then treat on a computer. Many of the systems that we talk about as sensors on Ethica are actually wireless interfaces. A wireless interface is a sensor that detects electromagnetic waves traveling through the air and turns them into electromagnetic waves traveling through a wire. Right? So basically what we're talking about here is a bunch of different kinds of antennas and amplifiers. There are 4 primary antenna-based systems on the smartphone. And by and large, from our point of view, the thing that they do is ping. Anyone know how submarine sonar works? Watched Hunt for Red October? Only one ping, please. I can't do a very good Sean Connery, but basically, in sonar, the submarine will, active sonar, the submarine will make a specific tone, go ping, and that ping will translate through the water out. It'll bounce off stuff, and then it'll come back, and you'll measure the response and figure out whether you're being chased by a Russian submarine or not. And it's a very similar kind of thing for a lot of the sensing we do of these wireless interfaces. We're looking at pings, but rather than pinging and waiting for the echo, although there has been some very gnarly stuff done at places like NIT in Eindhoven where they're actually trying to use Bluetooth as basically like an RF sonar. which is pretty wild and requires some very fancy mathematics. From our point of view, from Ethica's point of view, we have things that are actively pinging, and we're going to listen. And we're going to take the information from that ping and try and make some sense out of it. Simplest thing to do, because these RF pings are not just tones, they're actually little data packets, is to just look at what's in that data packet. And in that data packet is something about the name of the party that is pinging, something about their properties, and then this RSSI number, which you can think about basically as the number of bars. So if you've got a cell phone and you've cursed the fact you don't have enough bars, RSSI is reported primarily so that that can be displayed on the cell phone. There's some stuff that goes on in the background, too, about setting amplifiers and stuff like that for actually doing the signal processing. But we are going to basically use the ID of the other party and the RSSI that they are transmitting to us with, basically the signal strength, as sensors, when in fact they're intended to be used as a way of identifying things you might want to connect to, Wi-Fi routers, cell towers, and how good that connection is. So, as I said, there are four. I'm going to kind of do them in order of distance, reverse order of distance. So the shortest distance one is Bluetooth. There's a piece of trivia on each of these slides as well. For those of you who didn't know, Bluetooth is actually named after a Viking king. That Ericsson and Nokia were kind of prime drivers of this Bluetooth standard originally, and so they got it named after Harold. I think I got it written down here on the, can't see it because I don't have slide view, but there's a Viking king whose nickname was Bluetooth, and this is why we've got this kind of ruined-looking logo. So Bluetooth is short-range, low-throughput communication. It was initially designed for headphones. Just not put too fine a point on it. It was designed for wireless headphones and to tether your phone to your car, so you could do wireless, hands-off kind of stuff. It's moved on from there. There are lots of other things that speak Bluetooth now. Probably the biggest one is game controllers. So if you've got an Xbox One or a PlayStation 4, the game controller speaks Bluetooth back and forth with the system. Nominally, the range on a Bluetooth device is 10 meters. Although, effectively, it's probably closer to 3. You get kind of standing out in the middle of one of the fields in Saskatchewan, you can get 10 meters. Pretty much anywhere else where you start to get obfuscations of line of sight, this range reduces. And I'll talk a lot about line of sight. The other critical thing is because it's a low power signal, it doesn't transmit well through stuff. So Bluetooth has this idea of discoverable mode. And this is important for two reasons. One, it's important because it allows you to force a device to ping. And we can do this with Android devices. We can basically force them to sit there and ping at regular intervals so that we can trace contacts between participants by listening for them pinging for each other. It's also important from an ethics standpoint because you can't detect, using Ethica, Bluetooth devices which are not actively pinging. So anyone who is not in the study, who is not actively pinging, is undetectable. And by default, Bluetooth is off on most devices, most portable devices, because it's a bit of an energy hog. So you can say, by default, we won't be able to detect most people. And this makes ethics boards very happy, because people who are detectable have kind of specifically gone in and made themselves detectable. We can use phone proximity as a measure of interpersonal proximity. And this is kind of our primary use of this data. And we get graphs like this. So this is done from the SHED1 data set by Winchell. And so these are contact graphs aggregated by week for a set of like 39, 40 people who are grad students in computer science. And the interesting thing about these graphs is that they're kind of only quasi-static. Right? Week by week, kind of, if you want, yeah. The people who are kind of highly central still are fairly central, but the highest centrality person changes, and subtle changes happen in the network. For example, let's see, there's a very stable, or somewhat stable subnet here, 2933, but in this week, 33 isn't around as much and drops down and becomes a dyad with 29 with occasional appearances by 33. This kind of data has driven a lot of, it was one of the initial drivers for doing this whole work, and we are actually able to show that it matters when doing simulations of the spread of contagious disease. This is actually Mohammed's thesis from many years ago. This is basically contact data like the kind you saw, and what we've done here is we've had different ways of representing the contact patterns. So the dotted line is basically taking that contact graph and making it an aggregate graph and basically representing every edge as a probability and then drawing from those edges as probabilities. This one is actually treating each contact, each time step contact as a contact. So actually going down to, was there actually a contact at time X between A and B? And then these box plots represent different synthetic ways of doing things. So the first two very large ones are what we call the typical day approach, which is a very tempting thing to do. We're going to telemeter a whole bunch of people for one day, and then we're going to assume that that day is typical, and then we're just going to replicate that day through time and see how the disease spreads through this kind of cyclic contact pattern. And what we find here is that there's not much typical. Days are not very typical. There's a huge spread in the contact patterns day by day, which leads to a huge change in the amount of disease. It's a really bad assumption. These are various fits. So basically, synthetic networks generated from the contact probability distribution, kind of aggregated over the entire network, but with random contacts between people. So we randomly see the contacts, and then we draw kind of the probability of a duration. This is an example of two wrongs make a right. So in this one, it's actually the worst approximation, the poorest fit. It's a two-piece power law and with an exponential tail, which is often used for contact patterns, for contact durations. And what it does is it cuts off the even longer tail that is evident in the empirical data. But it does it in such a way that it gets rid of the fact that the ordering is not accounted for in the aggregate data. So in the aggregate data, you have a much higher chance of getting infected because you can be infected at any time of day. I don't see very many of you at 4 in the morning, but if I drew one of you sneezing at 4 in the morning, I'd just go back and consult what's the probability of our contact, independent of the time of day, and voila, infection occurs. So you get a much higher burden based on that. So by cutting out the most infectious contacts, the highest contacts in the tail, and then we compensate for the fact that it's an aggregate distribution and can infect at any time of day. So this kind of shows you can get the wrong answer, or you get the right answer with the wrong model. Okay, so that's how we can use Bluetooth. You can also use Bluetooth as a proxy for location, and as these kind of Apple beacons become more prevalent, that'll be more useful, but right now it's still kind of early days. For location, we typically use Wi-Fi. Wi-Fi actually stands for nothing. Everyone thinks it's an acronym. It's not. It's a play on hi-fi. And for those who are old enough, you actually remember what hi-fi means. Yeah, it tested well in focus groups, basically is what it comes down to. So there's your trivia for Wi-Fi. It actually means nothing. It's nominally 100 meters. So it's 10 times the range, 10 times the power of Bluetooth. Similar RF spectrum, though. So it has the same kind of properties in terms of how it goes through walls and stuff like that. But it's got twice as much power, or 10 times as much power, so it can go through more walls. Generally, for this, we're surveying routers. So there's one in this room somewhere, a little pod thing back here. Yeah, there it is. So we're looking for those guys. And this can be used as a proxy for where you are, or who you're in contact with more roughly, right? Because it gives you you think of it like a 100-meter circle. And so if you're both connected to the same router, then you're kind of within that same 100-meter circle. That's a long way to sneeze for the transmission of contagious disease, but it could be relevant for something like transmission of social norms. You're kind of occupying the same space. You're potentially cognizant of each other's presence. Primarily, though, it's used for physical location. And it's not just used for physical location by us. It's also used for physical location by Google and Apple. And I'll get a little bit more into that in a second. Here's a really interesting way of representing physical location. Anyone here in computer science? There's a few computer scientists. This is actually the Voronoi diagram of all of the Wi-Fi routers that we detected during one of our experiments and were able to cross-reference with a GPS location. So now we know approximately where that router is because we had a GPS read and a Wi-Fi read at the same time. So we can plop that Wi-Fi read down. And then what we can do is we can just draw little bounding polygons, where we kind of draw a straight line between any two routers. That's kind of the shortest path between the two routers. And we get this kind of bounding thing. And so you can be in any one of these cells, and it then becomes a representation of space. The interesting thing about this representation of space, though, it is not homogeneous. It depends on router density. So you can see up here at the university where there's lots and lots of routers, we can actually get incredibly dense maps of where you are compared to out here down in whatever it is, Casa Estates or whatever, where these large ranches with horses and things, and you've got one router in the ranch house, and then the rest of it's horse jumping and stuff like that. So that's one way of doing representations of space, and it's a very handy way. And it's often used, not necessarily with Wi-Fi, but with cell towers in a lot of mobility studies from cell records. So people can sometimes get the cellular records, especially in places like Africa and China, where the privacy laws are weaker, of a bunch of people who have been basically in contact with cell towers, and then they can trace their path through space by looking at the Voronoi diagram that cell towers make. Yeah. Yep.
Still get your map if you
Yep.
use Wi-Fi.
Yep.
Okay. I always thought that was weird and I didn't know how it worked. But
Okay, so basically what it is the Wi-Fi is pinging, right? Just like we said, it's I'm here, I'm a Wi-Fi, my name is U of S Secure 135, MAC address, long hexadecimal string. Would you like to connect? Right, here's my protocol. That's what it's doing over and over and over again. That's when you make your Wi-Fi at home visible, it's basically just sitting there pinging every few milliseconds, saying, hi, I'm here. This is my name. Would you like to connect? And then if you try and connect it, do you have the password, right? We just sit here and listen. You don't have to connect to it. You just have to sit there and listen to the pings because they're basically being broadcast in the clear, right? There's no encryption or anything. It's just, I'm here. This is my name. And so Google has been madly mapping these things, both by spying on you with your cell phone and uploading all of your GPS and Wi-Fi at a much lower resolution than we do, because they're really just concerned with building their big database. They might do it once an hour, just kind of wake up and grab a quick snapshot. And over the millions and millions of people who are using Android devices, that's actually pretty effective if all you're trying to do is find out where the Wi-Fi is. The other way they did it is they actually were actively scanning when they drove their Google cars around, recording where everyone's Wi-Fi was. And they had super accurate GPS on those cars. So they built up a very substantial database of Wi-Fi versus GPS locations. And I'll talk a little bit about how that works in the location stream in a second. We can actually do localization indoors too. This requires some fancy math. It requires a database of where all of those routers are to a high degree of accuracy. We've done this for the university. So if you've got an institution, if you're doing this in a hospital, you can actually go through, and we just use like a laser rangefinder and maps of the floor plan. You map out where each one of these routers is to the centimeter. You can actually get down to within 5 to 10 meters of accuracy indoors. That's not useful enough to give someone a map door to door. Being within 10 meters means you could be on the wrong hallway, but it is pretty good for understanding people flow, right, where people are moving throughout. And so this is an example of tracking students on their day-to-day activity on campus. This one requires a bit more effort, though. This is not an easily available feature within Ethica. Okay, so why is RSSI a problem? Why doesn't this work well? In class, I call this the ought problem. If you could come up with a reliable way to localize sub-meter from RSSI and Bluetooth and Wi-Fi routers, you would be able to sell the patent for enough to retire to your yacht. That it's that big of a deal, and large companies are throwing lots and lots of money at it. But it's limited by physics, implicitly. And really, it's limited by RSSI. So when you do these calculations, you're basically taking an RSSI, the amount of signal strength you've got from a particular beacon, something that's pinging, and you almost implicitly have to assume that it's line of sight, that there's a direct line between you and that router. And then from there, with some calibration, you come up with an estimate of how far it is from you to that router based on how signals attenuate in free space. Right? So now we've got a mapping between signal strength and distance. There's a problem with that mapping. The problem is that it scales exponentially. So every step you take, you have exponentially less signal. This is compounded by the fact that it's reported as an integer within Android and Apple. So basically, they're interested in displaying the number of bars. So they give you a number between 1 and whatever. But what that means is that every integer increment corresponds to a longer step in distance, because you've got this exponential relation. It's not linear. So we've already got a problem before we even start with the physics. The next problem is that radio waves transmit in many ways other than line of sight. For example, this lovely router on the ceiling can bounce off the floor to my receiver. This creates a path which is longer, and therefore returns a lower RSSI, but it also loses power in the reflection. So were I to compute my distance from the router with a line of sight assumption on this path, I would be somewhere over here probably. The same is true for Bluetooth. So when I'm looking at interpersonal contacts, it's difficult for me to tell exactly how far away I am. The other issue is transmission. So if I go out in the hallway, I can still connect to that router. It's got enough power to get through that wall. Even Bluetooth has enough power to get through, maybe not these kind of concrete walls, but certainly in a home where it's kind of classic North American timber and gyprock, Bluetooth can easily get through a wall or a floor. So you may have people in contact which are actually standing on different floors. You know, I'm in the living room, my wife is in the bedroom, it's directly above. We could be considered in contact by a Bluetooth. Weakly in contact, it's going to have a dissipation as it travels through that wall. But you have to be very careful with your interpretations. Interpreting contact. You cannot guarantee that any Bluetooth contact corresponds to a specific distance. This is usually dealt with in contact tracing by being very aggressive in what you consider contact. This actually works well for transmission of disease because you want to be within sneeze distance. And actually 10 meters is pretty long sneeze. So really, 1 to 3 meters is kind of the zone you're looking at for the transmission of disease, active transmission of disease. So you can be very aggressive. You can threshold your RSSI to a value which is very low. The other thing about RSSI is that it is a negative log number. So it's very difficult to interpret in the sense that it's like old school decibels on stereo systems. You get the decibels because you were cooler. So RSSI varies typically for a Wi-Fi signal from -30 to -100, where -30 is closest and -100 is farthest away. And this comes out of the formula you need to use to calculate decibels, because you have fractional numbers, so you get a negative log, and so on and so on. So just when you're looking, if you do look at the raw data for your RSSI values, and you go, why the heck is everything negative? It's because it's expressed in dBms. And there are formulas you can apply to get that out. But be careful when you interpret this. That's kind of the big thing. Oh, here's a graph to show you. So this is one of my students kind of standing about here, not in this room, but in a different room, but about this far from a router, just standing still for like 3 minutes. And these are all the RSSIs that were observed. Anywhere from a low of like -78 to a high of -39. And, well, there's a mean around -50, which in this case is probably right. But you can see it's a very peaky signal. It's multimodal. So you can't just say, well, take the peak or take the mean. Often what we do is we take the first peak. So we go back, we find the minimum or the smallest negative, and go more negative until we reach the first obvious peak, because that's least likely to be a reflection, most likely to be line of sight. Okay, so cellular. It's called cellular because the world is divided into cells served by a single station. Those cells have the Voronoi diagram shape I showed you earlier, except bigger, because there are fewer cells covering the world. We typically don't use this in Ethica because we've got Wi-Fi. But if you're doing rural, especially in places like Africa, this would be a much more useful signal because there's a lot more infrastructure in place for wireless telecoms via cellular than there is for Wi-Fi, especially in kind of suburban or rural areas. But it's basically the same thing. It's got a different frequency, though. It transmits at a different frequency. It goes through walls much better. It's much less impeded, but it's also kind of a 4-kilometer range, depending on the size of the cell, up to a 4-kilometer range. So you can get all kinds of different sizes and shapes depending on what tower you're looking at. Be very careful on how you interpret the data. Okay, probably the most important thing is that in many countries, having a cellular signal gives you access to AGPS, which is assisted GPS. Basically, there's an additional ping that goes out that tells you what satellites should be around and where you generally are to give your GPS a fighting chance to zone in. It basically gets your GPS fix faster. This only works if you've got a SIM card. So we've actually done a lot of experiments where we don't have SIM cards. We've just given out the phones and said, this is basically your measurement brick. Go forth and measure and answer questions. What it means is the GPS works slower. You don't get that quick fix that you're used to when you open up your own phone, because now it doesn't have that assistance. It's got to kind of lock in a more kind of traditional, slow manner. People often don't think of GPS as an antenna, but it is. Right? You've got to treat GPS, when you're thinking about its failure modes, as an antenna and not as a location. Because it fails not in the math to turn antenna-based measurements of distance into locations, but in failures in the way that that antenna is sensing the distance. So GPS is the only thing you'll ever use that actually has to account for relativity. The satellites are going around the Earth fast enough that there's a frame drag, which can be registered in the very accurate atomic clocks in these things. And so there's a little correction factor that gets put in there, which is kind of awesome. But basically, it's doing something called trilateration, which is the same thing we do with the Wi-Fi. It's a calculation, which is like triangulation, but using distances, not angles. So given a set of 4 points, where I know the distance between me and those points, and I know the locations of those 4 points, where is the only possible location for me to be? It's basically the intersection of 4 spheres. So you can solve for this. It's a really ugly, long equation. And it never works because you never get perfect enough signals that you are actually at one point at the intersection of 4 spheres. You kind of get an area smeared out, so you're probably somewhere around here. And then there's some fancy machine learning that goes on to provide input on that. Because it's coming from space, it has to go a long way. It's slightly different, though. It's actually doing a time of flight. So RSSI tries to equate signal strength with distance. That is not what GPS is doing. GPS is sending very accurate clock signals and then telling you, you are here. Right? Basically, time of flight. So you know the speed of light. You know how far or how long it took from these very accurate clock signals. It takes a very short amount of time, but we've got incredibly accurate clocks. And so then you know how far away you must be. V equal to d over t, basically. Because it's coming from space, though, it's a very weak signal. This has 2 important caveats, then. The first is it takes a lot of power because you need a big amplifier. You need a big amplifier in your phone, drawing a lot of juice to actually tease out this signal coming from space. The second thing is, because it's a weak signal, rebar is its enemy. Basically, as soon as it hits something made of metal, it's done. So as soon as you walk into an institutional building, your GPS is over. And maybe you stand near the window and kind of do this. You can get a fix again, but typically speaking, yeah, it's disappearing inside. The exception is, again, these kind of North American gyprock and wooden homes. You can actually get pretty decent reception inside older homes. If you've got a fancy new house with metal beams instead of wood beams, then again, your GPS is going to disappear. GPS has some interesting failure modes. This is participant 231, who shall not be named. Yeah, apparently he went to Saskatoon. Oh, I think that is Detroit? No. Toronto, for sure, and then somewhere in Minneapolis. Yeah. That's spring. The good news is, I don't know if you're doing filtering on this, Mohammed, or not, but this one's actually a pretty clean signal. 231 has got few outliers. Any outliers they have are local enough. However, you can get some very strange behaviors from GPS, and I'll throw this map up to give you a few pointers as things to look for which are wrong. Oh, there you go. So GPS also has an accuracy thing where it's like, I am confident to within X that you are here. So Mohammed has cleverly applied that to his visualization. If you look at the raw data, there are going to be things that are less confident. And if you graph them all, you get some very strange looking places. For example, here. And we call this the Nigerian Pirates. This is 0, 0, 0. Sea level, prime meridian, equator. When GPS gets really confused on a lot of the chipsets, it just throws up its hands and goes, I don't know, and returns 0, 0, 0. Your participants did not teleport to the middle of the Atlantic Ocean. The other way to do this often is we use what's called the speed filter. You know, are you violating relativity with this move, or traveling faster than 3 times the speed of sound. If that's the case, we can probably just get rid of that data point. So you get points like that's a very common one. For Saskatoon, there's another one down here, kind of off Tierra del Fuego, which I think is basically just flipping the north-south. So it gets confused for some reason about which hemisphere you're in, and will drop you off in the Pacific Ocean off the coast of Peru. Again, your participants did not teleport. Oh, you can see a nice smear here. I think, did you go down to Boston on that trip?
Probably that's where you started from.
Maybe.
Depends what the
Date range. Yeah. So there's some shadow there over Boston. You can see some shadows in the, this is an artifact of the visualization, actually. Okay. The other one that we see sometimes in Saskatoon, I don't know if it translates well to other places, but we get one of the satellites seems to be buggy. So there's a trajectory kind of like this, a grand arc across the map. That corresponds to the track of one particular satellite, which often gives erroneous readings. So you can teleport anywhere from Brazil to Nunavut along this kind of grand arc. The simplest way to deal with this is basically to filter by accuracy and filter by speed. So that gets rid of a lot of it, but does get rid of the local effects. The local effects become much harder, and I think, Andrew, you had one where you're like, I never visited this part of town. And, well, yeah, you didn't. GPS just got confused. And so you do have to take some of these things with a grain of salt. So Android supplies a number of logical sensors, and I believe that's the stream you're subscribing to, right? Location, not GPS, or both?
I get network and GPS separate.
Yeah, yeah. So if you look at the database, there'll be a column in there that has source, I can't remember what it's called, but something like that, and a provider. And it says either network or GPS. So because Google has been building up this massive database of Wi-Fi, and because GPS is slower and more energy intensive, they prefer to, if they can, get a GPS level accuracy measurement of where you are from the Wi-Fi, and then they fall back on GPS if they can't. And so you might see something that says basic network means it's based on the Wi-Fi. GPS means it's based on the GPS. It still has an error estimate. And that's basically what's going on there. So in dense areas from that Voronoi diagram, you can actually just say, I'm close to these routers, therefore I must be here, and you're done. This is actually, they've gotten a lot more confident over the last year. When we ran an experiment a year and a half ago, the split was about 70-30 in favor of GPS. Mostly it was GPS, but sometimes they would go to the network. Now, same location, Saskatoon, same general population, students. The experiment we ran in January, it was 80-20 in favor of network. So Google is very confident now in its ability to localize you based on Wi-Fi. This is a tiny caveat that's useful when reporting. When you report your locations in a paper, you should say that you got a Google location, not a GPS location. Because there's an 80% chance if you're in an urban area that that location was not from GPS. Okay, so the second class of sensors I'm going to talk about are these motion sensors. There are several sensors which detect different kinds of motion, how the phone moves. These were actually implemented as UI devices, right? The accelerometer on your phone that we've talked a lot about detecting activity, was really there so you could tilt your phone, right? That's what it's there for. It's there to detect phone tilt, and has been repurposed for all kinds of other things. Similarly with the gyroscope, magnetometer is basically there as a compass. I'll talk about each one of these things in turn. So these things are made with a technology called MEMS, which I did back in the day, which is awesome. It basically uses the same kind of fabrication techniques they used to make computer chips to make tiny, tiny, tiny machines.
So this is a picture of an early accelerometer prototype. The one inside your phone is much more complex. But it's pretty simple. It's basically a mass and some springs and fingers, interdigitated fingers, and basically you detect the distance between the fingers by the capacitance that is created between this very small air gap. So each of these fingers is approximately 2 microns wide, where a micron is 1,000th of a millimeter. So this entire device is smaller than the width of a human hair. And that's how we can make them so cheap and reliable, is that they're incredibly precise and incredibly small, so you can manufacture millions of them on a single wafer at a single time. And this is why you've got cheap sensors everywhere now, this MEMS technique. Unfortunately, the accelerometer is lying to you. The accelerometer does not detect acceleration. The accelerometer is a force sensor. It detects the force exerted on a known mass against a known spring. This is why it detects gravity, even though it isn't moving. If you hold your phone and you rotate it, what's actually doing is detecting where acceleration due to gravity is, where that gravity vector is pointing. It is sensitive to that gravity vector because it is sensitive to forces. This is the first thing to think about, that it's actually a force sensor, not an acceleration sensor. It does this in 3 axes, x, y, and z, although often it's reported or used as the norm, so it's square root of x squared plus y squared plus z squared. When you're interpreting raw accelerometer data, you must account for gravity. So this matters, for example, when you're trying to do pedometry with the phone in different places. Movement changes if the phone is on a hip, center of mass, versus an arm. Right? As I swing my arm, I get a pendulum motion with respect to gravity. As I move my hip, I don't. This changes basically the amount of energy that is detected by the accelerometer. So you must account for gravity before you do your pedometry. The good news is, because it's sensitive to gravity, and because it's fairly easy to detect gravity, for those of you who carry, use a low-pass filter or a moving average filter, we can figure out the orientation of the phone with respect to gravity, which is the surface of the Earth, which can be very handy. The magnetometer is on there to make the compass work, but it's a magnetometer. It senses magnetic fields. This means that it's also a very good metal detector. There's a neat trick you can do. You can get your phone out, launch the compass app, stand next to a metal filing cabinet, and move it. And you can watch your needle swing to the side. So very clever folks at MIT actually use this to detect when you're in a car, basically based on the fact that there's a big swing in the compass needle as you get in the car, and it kind of re-equilibrates. Yeah, whatever. So it's very noisy. It's very sensitive to the environment. But for slowly changing direction, you can kind of average out over a long enough period of time, it can give you a decent answer, unless someone's left it on top of the filing cabinet, in which case, Then finally, the gyroscope. The gyroscope is a very funky device which has all kinds of stuff going on in it. But basically, it detects how the phone is turning. It detects rotational velocity. You should never have to use the gyroscope signal. It's there to fix the accelerometer and the magnetometer. It's a third point of data about, is the phone rotating? So if your magnetometer is doing this, but the phone isn't moving, then you can say, okay, this is due to magnetic interference, some filing cabinet over there, right? If you're doing more advanced signal analysis, you go back to this as kind of an additional stream. For most of you, you will not deal directly with the magnetometer or the gyroscope. You will subscribe to the orientation stream, which is basically Google's, this is the pose of the phone. using the accelerometer, the magnetometer, and the gyroscope. So these are great. They tell you what people are doing. But the signals themselves are almost useless. They all require a great deal of analysis to make sense out of. So there's a couple of streams you can look at. I told you about the orientation stream. I don't know, do you have that one active? Yeah. And then the activity stream, Google Activities.
No, it's separation of user acceleration versus gravity.
Yeah. So user acceleration versus gravity is done for you already. There is another stream that Mohammed may or may not implement in the future, which is Google's attempt to do this walking, running, sitting, biking thing. It's totally flaky. I don't trust it, except for not sitting. That's pretty much as far as I would trust that particular stream. And that one isn't hard to do. And as I'll talk about a little bit later, once you've got this kind of data, then you've got to determine how you're going to treat it, how you're going to aggregate it. This is a big decision. You can get incredibly, well, basically you can prove whatever you want. This is what I've come to the decision of. I'm working on some stuff with Nazim's data, the kids' data. We just completed the runs. I've got to go through and look at it. But it seems to me that for every hypothesis you could make about activity, we could pick a spot in the plausible thresholds for what constitutes active and inactive and come up with an answer that we wanted. Yeah. Yeah. To look at the data a little more carefully, but yeah. It seems that, so this is like p-hacking to a whole another level. You can start hacking even before you start doing the statistics. You can basically bias your, well, if we tweak, the definition of active by 10%, then I'll get the answer I want. And p less than 0.05, therefore it's true. So you do have to be very careful about how you determine, how you operationalize the analysis of these sensors. Okay. The one thing I want to take away from this, sensor data is truthiness, but it is a different kind of truthiness than the survey data. It is not truth. It is a transducer, which is noisy and confounded by all kinds of interesting physical properties. Just because the phone said you were here does not mean you were here. You did not teleport to Tierra del Fuego. And yeah, we'll talk about analysis later today. All right. Any questions? No? Okay. We'll move on to the next thing. Sorry about that. Took longer than I thought.
Okay. I guess one question. How can you guard against those outliers, those new points when you're looking at the data streams that you've been? For example, I knew that I wasn't in that area when I looked at my data, but of course when you get into pure categorizing people study, how can you sort of guard it? Do you sort of look at outliers and disregard outliers?
So the answer is, of course, it depends. Usually you've got like almost like a triage that you do, right? So first you triage by accuracy, right? You get rid of all the stuff that even GPS doesn't believe. Then you triage by speed. What do I know about my participants that would imply, how fast they can possibly travel, right? Once you're past that, though, you have to start being very careful because it depends on the kind of analysis you're doing. If you're doing analysis of, for example, activity spaces, then you can probably do outlier removal in a traditional statistical sense because these kind of rare trips taken to different places do not constitute part of an activity space, right? So you can just kind of ignore them. just kind of do traditional kind of toss out everything that's 2 standard deviations from the mean or whatever. If, however, you're looking at kind of scope of movement kind of things, if you're trying to generate distributions of travel distances, what is the probability someone's going to travel a certain distance, then those outliers become important because they're part of the tail. So then you have to start deciding how aggressive do you feel comfortable being.
And I guess start using social networks or proximities, get confused as well. Outlier information that someone's not actually there, but then that is associated with someone being in that, someone else in the network being there at the same time. Is that right?
Yeah, so I mean, it depends on how you. There's lots of different ways of measuring contact, like we said, right? You can do it directly with Bluetooth. You can do it. You connect to the same Wi-Fi. You could grid the Earth and look at the location and see are you in the same grid. One of the benefits of this kind of data is velocity. You've got high temporal fidelity. So what you can do is you can start looking at longer chunks of time and looking for the probability in that chunk that this is true, and then come up with either, and this is something that is a pet project of mine that will take years, grinding through that whole analysis entirely with the probabilities and distributions. Or you can have a threshold, basically. If the probability is greater than this, then we assume that this contact is true. Anything else?
And there's some analysis on GPS data specifically that I think, some analysis requires more GPS data in the sense of where the person is located, but some analysis I think can benefit more from the already processed GPS data. So because you don't necessarily need the raw location data, but you need the, for example, you need the places visited during the day, which you can, which I think there can be some algorithm that can analyze the GPS data and give you that, and that's what you're interested in, and not necessarily their trajectory. You're just interested in the location they are visiting. Or the other sort is the heat map, the frequency of them visiting different places. You can the location data itself, but you're interested in the frequency of them visiting different places. Yeah, and then probably like some of these outliers are easier to detect and skip them in some of these analysis, so they become less important. Unless that outlier is actually like the place that they have seen once. And how important the place that they have seen once is, that's a whole different question.
Yeah, so it really depends on what you're trying to do. So for example, if you're looking at trying to build a histogram of place types, right, so you break this data into tables for all the things that are near this location. You have a histogram for all the things that are near. And you can be a lot more inclusive because those weird teleports aren't going to take you in things very off the ship that you'll have an error that leads to a lineage.
So Kevin, I just put your thumb drive there. Audio test, 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 test.